In this section, we're going to be combining several of the different things that we've looked at in this semester so far. In particular, we're going to be looking at one other thing, though, and that is complex numbers. So just a reminder first to start off with, when we talk about complex numbers, we're talking about numbers of the form a plus bi, where a is a real number, as is b. We call this component the real component, and we call the bi component the imaginary component. And the first thing we're going to take a look at is what a complex plane is. And a complex plane is simply an axis where complex numbers, a plus bi, have a visual representation. The complex number z equals x plus yi has a real number component x and an imaginary y. This imaginary component y. This corresponds to xy on the standard axis. The real axis is the horizontal axis that corresponds to the real coefficient x described above, and the imaginary plane, imaginary axis, let's fix that real quick. Is the vertical axis that corresponds to the imaginary component y. And this up here with the imaginary component as well. A little bit of a typo there. All right, so the visual imagery that we have is that we have this xy plane, much like we've always used before, except that at this point we're going to refer to this as the real axis, and this is our imaginary axis. And the first thing we want to do is we actually want to plot a point. And this actually doesn't just ask us to plot a point. It asks us to plot the point. So that's the first thing. To write it in polar form, which we'll talk about how we do that. And then the third thing is to express the argument, which I haven't yet told you about, in degrees. All right, so the first thing we're going to do, as I said, is to write this or plot this in the complex plane. First thing, though, is that the square root of 3, this is approximately 1.7. So if we're taking a look, this will be in quadrant 4, because this is going to correspond to the point 1 and then 1.7 negative. So we have our axes, and we have, we're going to mark our axes out in 2 in each direction. Alright, so we're going to go over to 1 on the x-axis and down to negative 1.7 for the y-axis, and so we're roughly at this point right here. So this is my coordinate, if you want to call this. You could say that this is z equals, so this is my point z. We'll give it a name. Alright, so what I'd like for us to do is to first convert this to polar coordinates without the official sort of ideas of doing so. So remember, polar coordinates have 2 components. They have r, let me use a different color here, which would be the distance from the pole, or the origin here, out to z, and then they have the angle theta, which is going to be measured right here. Alright, so let's start with finding r. And the way I want to sort of remind you how to do this has to do with triangles. Since we haven't talked about those in a while, this is a really nice time for us to take a look. This actually forms a wonderful right triangle. And it's a right triangle with some specific lengths. This length in the horizontal direction is 1, and then the length in the vertical direction is actually square root of 3. Or more specifically, negative square root of 3. And that might ring a bell to you as to a familiar triangle. If it doesn't, you can always use the Pythagorean theorem to find the third side. But this is a very familiar triangle. It is is 2 on the hypotenuse, and that should ring a bell for special triangles, as well as what your whole unit circle was built on, which is 30, 60, 90 and 45, 45, 90 special triangles. This is a 30, 60, 90 triangle, and the angle here at the top that we are interested in is the 60-degree angle. If you are trying to remember which one's which, you can actually think about the fact that the square root of 3 is a bigger number than 1, so it has to be across from the bigger angle, hence the 60-degree angle. Now, both of those pieces of information are useful pieces of information, because if you take a look down here, back at my regular triangle, this is 60 degrees. Well, that piece being 60 degrees means that this outer piece over here would have to have the 300 degrees. In addition, the hypotenuse length that we found up here is my value r. So my polar coordinate is actually r equals, and I have is the coordinate 2, and then 300 for my, let me write this a little bit differently. My polar coordinate is r theta. There we go. So this is this was part 1, or part A, right? This was part B, writing it in polar coordinates, or part 2. And then part 3 was finding the argument, and the argument is actually the angle measure. So the argument is the 300 degrees.